Okay, so lesson 11 is actually our first lesson that incorporates a calculus standard, believe it or not. Okay, and now I think we go back tomorrow and there's no calculus standards again, but so we start looking at limits. We have three big topics in calculus. Limits is one of those three big topics. You learned a little bit about limits last year in pre-cal, if I recall. So we're going to do a lot with limits. We'll also learn about derivatives, and we'll also learn about integrals. Okay? Now, in order to talk about limits, and even derivatives and integrals, continuity is a huge topic in calculus as well. Okay? So we need to talk about what does it mean for a function to be continuous. I mean, I think hopefully you have just generically with the word continuous, you have an idea of what continuous means, I hope, you know. So notice here, a function is continuous on an interval between the x values a and b if the function is defined for all values of x between a and b, and if a small change in x does not produce a sudden jump in the value of y. Okay, so that's putting it into words, which I get is a little confusing, but I mean, key things here it talks about it's defined for all values. So if our interval is from a to b, okay, that's like saying if our interval is from 0 to 10 or whatever. But if any x value you put in will produce some output, then it's defined. Okay? Now, if a function is not continuous at a value, so if you can find a value that you can't put in, then we say that the function has a discontinuity, or it's discontinuous at that value of x. These pictures are examples of discontinuities. So, need to be familiar, and this is picture-wise. We'll also, as time passes, look at equation-wise. But discontinuity. I like to think about a graph is not continuous if I have to pick up my pencil or pen, right? If I can't just keep drawing my curve, there's a discontinuity there. Yeah, so anytime there's a vertical asymptote, your graph is discontinuous. It is not continuous right here. It's discontinuous at A because those on both sides of A, it's going up to positive infinity, but they're not going to eventually touch. They're going to get infinitely small, infinitely close, or what, infinitesimal, or I can't think of the word I want there, but, they're going to get really close, but they're not going to touch. On g of x here, discontinuous at b. We've got one side going down, the other side going up. They're going to get close, but at that b value, my graph is discontinuous. C, there's a jump there, right? Okay, so that's an example of discontinuous. Now, that's an example where technically every value you put into your function would work, but this falls into the category if there is a sudden jump. Okay, so because every value I put in, because C right here has a closed circle up here, open circle here, every value I put in is going to work, but there's that sudden jump. D, or M of x, has a discontinuity at D because there's that one spot that I would not get a value for. And then N, discontinuity at E. Again, I'd have to pick up my pencil to draw that other dot, so that falls into the sudden jump category. So those are all visual examples of discontinuity. Now, let's see, I think I've already covered all this, haven't I? The A and B graphs both have what are called vertical asymptotes. These are vertical lines that are approached but never touched by the graph of the function. Do you remember when vertical asymptotes happen in an equation, like in a function? As I look at a function or equation, how do I know there's going to be a vertical asymptote? Or how do I find where that vertical asymptote is? Okay, so it has to do with the denominator. If there's a spot that would make the denominator equal to 0. So, like right here, this would be having x minus a in the denominator. If I had a factor x minus a in the denominator, that right there tells me there's a vertical asymptote. So it's all about that denominator, right? Denominator or vertical asymptote equal to 0 is your denominator. Or, I think I just totally said that backwards. But you knew what I meant, right? Okay. left hand and right hand limits. As I talked about, one of our big three is limits. And notice it says there, study of calculus is based on a concept called the limit of a function. The limit of a function is the number that the value of the function approaches as x gets very close to some designated number. Okay? Two of the most important limits concern the values of the following expressions as the value of x gets closer and closer to 0. So, what I want to do here, so let's grab the calculators, and I want to look at some values here. Now, first of all, it's 1 plus x, and that exponent, can you guys read that exponent? It is 1 over x. I'm not sure I could read that, honestly.
I could.
Granted, I've got the older eyes, and, I've hit that point where I don't need reading, well, I don't usually need reading glasses quite yet, but there are times that it's right there. Okay, so what I want to look at is as x gets, what do we talk about? Closer and closer to 0, yes? So, let's start with 1. If you put in 1, I don't think if I've done this in a chart in the past or if I've just done it like this. If we put in 1, what are we going to get here? 2. Okay? Let's put in 0.1. Because I'm trying to get closer to 0, right? So that's, if you want to, 1 plus 0.1 in parentheses raised to the 1 divided by 0.1, right? Did you get a lovely decimal like mine? .5937. Okay. Can we move the decimal over again? What if my input is 0.01? Now, you guys can arrow up and copy this and insert, right? I don't know how talented you guys are now. If it's 0.1 and I want to put a 0 there, you know how you can use insert? Go second, and that delete button right above delete is insert, and so it will insert a character. So second, insert, and then I just insert a character. I can do that in the denominator, or I can just retype here. So this time, what do I have? .7048. What do you think I'm going to plug in this time? 0.01. I probably should have done this in the list is what I probably should have done. And I didn't. Oh well. .7169. Let's go one more time here on the positive side. Going to insert a 0. Type in another 0 in the denominator. 2.7181. Okay, now, when we look at limits, these were all positive values, yes? So if you think about it, these are all values as we approach 0 from which side? That's as we approach from the right, yes? As we approach from the right, and we're getting closer and closer to 0, that's what my value is doing, right? My y value is getting closer and closer to, right now, what do I have, 2.7181? Obviously, we've got the 2.7 part, maybe even the 2.71 part, right? We don't know exactly past there. Let's see what's doing from the negative side. So let's start at, well, we'll go ahead and do -1, I guess. But you're going to run into a problem because 1 plus -1 is 0. I don't even think, does Calculator give you error on this one, I feel like? Because you'd be doing what, 0 to the -1 power? Yeah. So right there, we can't do that value. However, we can do the others. So let's do the equivalent negatives. Let's do -1/10, -100th, -1,000th, -1/10,000th. But you really could take your values from above and just plug in negatives, couldn't you? Whoops, that's not the one I wanted. Oh, I give up. So I can insert a negative here. Okay. -1/10. Did you get something eventually? Maybe you're just retyping it in. I'm just going to say 2.867, but really it rounds to 2.868. Now do -100th instead of a 10th. .7319, but really goes up to 2. Plug in -1,000. .7196. -1/10,000 and 2.7184. Okay. So what we were doing, we were letting x get extremely close to 0. Technically, we could keep going closer and closer to 0, couldn't we? What is this value? What is the value, the output value, getting closer to? Okay, 2.718 something. 2.718 ring any bells? E. Okay, this output is getting closer and closer to E. If you remember E, it's the natural number that we use with logs, and E is officially 2.718281828, if I have that written down right. At least that's what my calculator shows. Okay, so being able to examine, this is something we have to be able to do in calculus, being able to examine, looking at both sides, seeing what it's looking like. If I graph this, I'm going to graph this for you real quick. Okay, so right there, oops, as x is getting closer to 0, where is that on my graph? Where is x getting closer to 0? Where is the value x equals 0? X equals 0 is before we move left or right, yes? So the idea is here as x approaches 0, so as x is getting closer and closer to 0 from the left and the right, what is that y value that we're getting closer and closer to? And so if I do a trace, well, first of all, you'll notice, does it actually exist at that point? And it's showing it doesn't exist at that point. But if you trace left or right, you're going to have values very close to it, although not as close as ours were. 2.537, 2.95. that would be a hard one to get exactly off of the graph, which is why looking at it by hand was more helpful. But that's the idea. As x approaches 0, my graph is getting closer and closer to that 2.7 number, or an e.
Does yours have little dots on the left side?
What do you mean?
Mine has little dots.
Is that an asymptote, maybe?
I don't think so.
There would be an asymptote. I have no idea what that is. I have no idea. I wonder if there's some setting there. Do you have something turned on your graph that
You have got one.
do you have the little dots
I have,
like over on the left below the y-axis?
yeah, I have one.
Into table set there. Second table set. No, that's not. Sorry, second. Sorry.
That's so long.
I have the dots as well. Little boy. The chicken house.
I'm trying to think, what's the different setting? Because I don't see anything unless just curious now.
Really? What's that? I have multiple dots. What'd you put?
Yeah, that's Daryl has multiple dots too. Why do I not have any dots?
Did you put like an actual number? No. That's what yeah, that's what I put in the equation.
I got one thought on something I did differently.
Oh, I got one many dots.
Okay, here's the difference. I now have dots. I didn't have dots earlier. I don't understand the difference as to why it did this, but the first time when I did my x one, I just typed 1 divided by x.
That's what I did.
And now I went back and changed it because I noticed Daryl's was different, and I used the fraction notation and did 1 over x.
Yep.
I have no idea about the dots.
Yeah, 1 divided by x gives you like 1 dot.
So maybe I had 1 dot and I just couldn't, maybe I thought it was dirt on my calculator. But interesting. I don't, so I don't know.
I mean, everything else is the same with both of them except for there's less dots.
Okay. Sorry, your teacher's mystified. I'm not sure what the dots are.
I like them.
I mean, I did just try and put in like -4 because like -4 is a spot where the dots are, right?
Yeah.
I plugged in -4 into the equation and you get an imaginary answer.
Yeah.
So, but
What about negative 5?
anything over there you would get a negative answer, I think. Or an imaginary answer, excuse me. So, anyways, yeah, I don't know.
That's strange.
It is. It's interesting. Okay, let's look at our other one. Sine x over x. First of all, in order to do anything with sine x over x, what setting should your calculator be in? Radians. Calculus is going to require radians most of the time.
-5 does actually have an answer for y.
Oh, it does?
Yeah. Like it
Oh,
goes like that, and then
maybe because it's odd.
you can actually trace them.
Yeah, there's nothing on the graph at -4.
But there is on -5.
Yeah, I don't know. I'm sorry. I don't have a better answer for you on that one. I'd have to think about that one. Okay. So, if we do sine x over x, I'm not going to go start as far out as 1. I was going to use 1/10, 100th, and 1,000th. In the negatives, I was going to do the same thing. -10th, -100th, -1,000th. This one will be more obvious as to what it's approaching. So, sine of 0.1 in parentheses divided by 0.1, 0.9983. Is that what you guys got for your first one if you're trying it? Sine of 1/100th divided by 1/100th. Technically, it's 0.99998 if you go another spot, right? 4 9s and an 8. Sine of 1,000th divided by 1,000th. What do we have there? A bunch of 9s. What are we getting closer to on this side? Yeah, that essentially rounds to 1, doesn't it? I'm going to go ahead and write 1 because I only have so much room and I can't get all those 9s in. What's happening if you do the negatives? Sine of negative 1/10 divided by negative 1/10. Same number, 0.9983. So take a guess. Sine of negative 100 divided by negative 100. That's the 4 9s before it turns to something else. Can you guess what's going to happen next? Yeah. Sine of negative 1,000th divided by, negative 1,000th. Then we're back to more 9s than I really have room to write. I guess I could in this case, but, If we kept going, what do you think the graph's getting closer and closer to? 1. Okay. Now, if I graph this one, sine x divided by x. Okay. Lovely glare up there that I'm trying to avoid. Okay, guys. As x approaches 0, so where am I walking towards? As x approaches 0, we're going to the y-axis, right? That's where x equals 0. So when x equals 0, what's my graph doing? It's going up to approximately what? 1. If you hit trace, okay, again, it doesn't actually exist at 0 because you can't divide by 0, right? It'd be sine of 0, which is 0 divided by 0, doesn't happen. But if you arrow left or right, you're going to have numbers that are increasingly closer to 1, okay? In order to talk a limit, it doesn't have to exist at that value. It just has to be getting closer and closer to that value. So you'll notice down below it talks about, we use the idea of moving along the graphs as we approach the x out value specified. So, we're walking closer and closer to that x equals 0. Limit answers always correspond to y values. So it's always what would that output be? Okay. Let's get back to the back part, which is a little more fun. Yes, I called it fun, but I think you'll like it. Because now we're going to actually just practice doing some limits. That was kind of the investigative, okay, let's practice. So for this first A, B, C, D, there's a lovely graph off to the right, yes? It's a lovely graph, but you know what? That's all right. It still works for what we need. So, I think we talked about this last year. The limit, as x approaches 5, what's that plus sign after the 5 mean? From the positive side. So from the positive side will always mean from the right. So we want to know the limit as x approaches 5 from the right of this function. So as x approaches 5, that's as we approach the x value of 5 from the right, what is the y value? So, okay, let me find 5. Have you figured out the answer here? Now, they're going to start us off tricky right away. 5 is right here where there's a big old break in the graph, isn't there? Which piece of the graph do I need to look at? The top one, because we're approaching from the right. So as I'm following my graph from the right, as x gets 5, what y value am I approaching? The y value of 40. The graph doesn't have to exist at 40. It's just approaching that value. So it's getting closer and closer, like 39.9999999, you know.
Yeah.
Okay, so you guys remember that as x approaches 5 from the right? Okay, and I guess I will comment that this is as x approaches 5 from the right. That's the vocabulary I use there. Okay, so what's different about B? Limit as x approaches 5 from the negative side, which is the left. So this is going to be from the left. Okay, so here's my x value 5. This time I'm looking at the left piece, yes? As we approach from the left, as I get closer and closer to the x value of 5, what's my y value doing? 30. You okay with those numbers?
What's the point of the 29 being 1?
I think maybe just to show that it exists. I honestly don't know. Well, I was going to say it's probably trying to trick you into saying 29 because 29 is the value that actually exists. But a limit does not have to exist at that value. Okay? It's approaching that value. It doesn't have to exist. Okay, so C, this is the limit as x approaches 3 from the right. So, here's my x value of 3. As x approaches from the right, what do you think? What is that corresponding y value? 20. What about as x approaches 3 from the left? Still 20. Because that graph, there's nothing funky going on at that graph, is it? It's meeting both sides, left and right, 20. Remember I talked about being continuous at the beginning? The difference is my graph is continuous at 3, my graph is not continuous at 5. Yes?
Isn't there a dot?
Okay. I didn't even notice that, honestly. Okay. Okay, so I give you credit. There is a dot. However, it doesn't change my answer. Okay, so limit. I get it. And that's a valid point. Honestly, I didn't even notice that 3 was down there. That dot was down there. So I don't know if I've ever noticed that one is down there. I don't know if anyone's ever pointed out to me over the years. But it's a valid point because here's the idea. It's not about other values. It's about what is the graph approaching. And so what is the value that we are approaching? And we are approaching that 20 there. And so that's the answer I want because it's a limit. Now, it's odd though because there's no like open hole there. So I don't know if that means there's 2 values at 3, for this particular graph, function. But yeah, where it would matter, like where something would matter like this. So like 5, we already talked about the limits, yes? If I was trying to find the value of the graph at x equals 5, if one of these was filled in and one of them was not, then that would determine which one it was. But the limit still exists the same because it's just as you approach. You can't jump to a limit. Does that make sense? Good question. Okay. The limit of f of x as x approaches some number a from the right or from the left is the number f of x gets closer and closer to as x gets closer and closer to a. When discussing limits, we do not even consider the value of f of x where x equals a. And that's one where Trevor pointed out that dot there. I get it, it's a value, it's an output, but it doesn't matter when we talk limits. Okay? So, we have a new graph. Limit of f of x as x approaches 3 positively. So from the right. I have a 2. Are we okay with 2? We're going from the right. So here's my x equals 3. So which part is coming in from the right? And that's going to be that part right there, yes? And so then what you want to figure out is when x equals 3, what is the corresponding y value? And that is 2. Good? What about as x approaches 3 from the negative, from the left? So this time, I'm looking at this bottom part of 3 because now my graph is leading in from the left down here. And it leads me to that right there. So what y value is that at? That's a y value of 1. Okay? Limit of f of x as x approaches 1 from the left. So here's 1. What did you think? 1, because as we approach from the left, it's bringing me down to 1. Limit of f of x as x approaches 1 from the right. So again, x value of 1. My graph is coming from below up here to 2. I kind of like those because they're kind of fun, right? Maybe fun's not the right word, but which makes them fun. Maybe not. Okay.
It makes them prefer to everything.
Okay. Well, you're talking to the math teacher here, so.
Taking a rectangular prism and either having a surface area or going and getting to the other.
Okay. Example 11.2. Limit as x approaches 3 from the right of f of x. What do you think? So I'm looking right here, and I only have one line here, right? Nothing fancy going on. So when x equals 3 here, and it's coming from which way? From the right. So we're coming up from down below, yes? What is that y value we are approximately equivalent to? I would agree with 40. What about when we approach from the left? Yeah. As we approach from the left, it's just coming from above, but it's still going to approach that same value because this graph is a continuous graph.
It also says estimate, so.
And it is estimating because the way that graph is, technically, can we tell exactly? I mean, it's a pretty decent 40, but okay. Given f of x equals 1 when x is greater than or equal to 0, and negative 1 when x is less than 0, sketch the graph of f and find the following two limits. Okay. We talked last week one day about piecewise functions, right? That's what we have here. We have a piecewise function. Now, that helps. F of x, what's another name for f of x? Y. So where it says f of x equals 1 or negative 1, those are really the equations y equals 1 and y equals negative 1, yes? So y equals 1. What does the line y equals 1 look like? Horizontal line that cuts through the y-axis at 1. Now, when is that part of the graph true? When x is greater than or equal to 0. So when is that? Okay, so it's this horizontal line, but I'm not going to draw the horizontal line all the way across. I only want to draw it when x is positive. So to the right of the y-axis. So there's that top part. Y equals 1 when x is positive, greater than or equal to 0. What's the other part of this piecewise function? Y equals negative 1 What's the y equals negative 1 look like? So negative 1, it's still a horizontal line, but this time it's
And there's an open circle, right?
down at negative 1, and it's when for all values of x that are less than 0, so when x is negative. No! I probably didn't get that quick enough, but. And I think Mallory said it. What do I have to put here?
An open circle.
An open circle. Because we have to define that value one place or the other. So my graph looks something like that. Now, are we set up to answer those limit questions?
Yep.
The limit, as x approaches 0, from the right. What's my graph doing? X approaches 0 is the y-axis, right? What y value is my graph approaching from the right? 1. What about when x approaches 0 from the left? So we're approaching the y-axis from the left, and my y value is negative 1. Does it matter that it doesn't equal here? No, it's just what is it approaching? And it's approaching the value of negative 1. It won't actually equal it, but a limit doesn't have to equal it. Okay. Good news is you will have some that easy.
This is right there. I think I left my homework at home. If I have someone bring it like during school, can I come get it checked, or would you rather me just come tomorrow and give it to you?
I think it. I think I did it right. I don't care about any of the others.